Okay, so in our last class, um, we ended our discussion on the open sets. So let me quickly recap where we're at. So we were talking about these things called open sets, and we saw that the idea of an open set came from something called interior points. So interior points. And that is if every single point in a set is an interior point, then we say that the set is an open set. And the picture, so although this is we we are doing our work in one dimension, that is just R, and this is a two-dimensional picture. This is the picture you should have in your mind. So you have some set A and an interior point of A. First of all, the point must belong to A. So X must belong to A. And we say that X is an interior point of A if it is possible to put just one neighborhood. So you just need to find one neighborhood. There might be many, but you just need to find one neighborhood of some radius epsilon. So this is the neighborhood, centered X, radius epsilon, that is completely inside of the set. So the idea is, so when you hear the word interior, you should think about you are completely inside the set. So how to say a point is completely inside the set? You need to say that it is possible to wrap a neighborhood around that point that falls completely inside the set. And a set is open. So open sets mean that every point is an interior point. So a set is open if every single point you could do this. So now we're going to look at another side of things, something called the closed set. The closed sets today. Okay, and just like the open set dealt with a certain type of point called the interior point, we will see later on that the closed sets deals with another type of point, not interior points. These points are called limit points. Okay, so open sets deals with interior points and closed sets deals with limit points. We'll see in a bit what exactly is a limit point. And a set is said to be open if every point is an interior point. So in a similar way, a set is said to be closed if not every point is a limit point, it contains all its limit points. Right? Whatever that means, we'll see in a bit what it means. So we're going to talk about the closed sets today and limit points. Now, the first definition that we'll see in a few minutes does not have anything to do with limit points. So I said here a set is closed if it contains all its limit points. But there's actually another way of defining what a closed set is without even talking about these limit points. So we'll see in a bit that you could define what closed sets are in terms of these things called limit points. But for now, it turns out that you could actually define what a closed set is using open sets. Okay, so we know what an open set is. We're going to now define the closed sets using the open sets. So once you know what the open sets are, that allows you to talk about which sets are also closed. And the idea is very easy. A set is closed if its complement is open. Okay, so the relationship between the open sets and the closed sets is that they are complements of each other. Right? Complements. And of course, you know what the complement of a set is. So A complement is just equal to the entire space. So for us, it's the real numbers minus A. Okay, or is the set of all real numbers such that these elements do not belong to A. Okay, and I'll give you all the picture for it. So let's use this picture over here. Okay, so if this is some big space X and that set is A complement is everything outside here. Okay, so the complement is everything outside of the set. So this is the set A complement. So given any set, you always have its complement. Okay, so that's the outline for today. Okay, so let's get into the actual definitions of things. So now that we've looked at the interior points and the open sets, we're now going to turn our attention to limit points and the closed sets. Now, the most common mistake in this part of the course, or maybe in this entire course, is this. If a set is not open, so when we were figuring out whether or not a set is open, and if it turns out the set is not open, you might be tempted to then write it's a closed set. Or if a set is not closed, you might be tempted to write that the set is open. Now, what's written here in red is wrong. So if a set is not open, that does not mean it is closed. You cannot write that. And if a set is not closed, then you cannot write the set is an open set. Okay, and I put here, as you will soon see, sets can come in all possible combinations. So a set could be open and closed at the same time. A set could be not open and not closed. So none of those. A set could be open but not closed, and a set could be closed but not open. So when it comes to sets, it could be anyone, right? Anything goes. So what I'm trying to say is that if you know a set is not open, then you cannot just conclude it's closed, right? It might be closed, it might not be closed. You need to show something else, okay? Or if a set is not closed, you cannot then just write, okay, well, then it must be open. No, then you need to show something else. Okay, so these things do not follow from each other. Okay, so what exactly are these closed sets that I keep talking about? So a set A, which of course we live in R, so everything is taking place in the real numbers. Okay, but so a set A, which is a subset of R, is said to be a closed set if its complement is open. So this definition, for now, in order to check whether or not a set is closed, what we need to do first is take the complement of it and form this new set, A complement. And then we need to ask ourselves, is A complement an open set? Because we know what open sets are. Open sets mean every point is an interior point. If it so happens that A complement is indeed open, then the original set A is closed. If A complement is not open, then the original set is not closed. Okay, so before I go on, let me just write that here. Okay, so write it down here. So what we have from that definition is definition, if A complement is, so put open, right? That means that the original set A is closed, right? And it's an if and only if statement. So from this, we also have this point. So now you're saying, okay, but what if A complement is not open, right? Could I conclude anything about the original set A? And the answer is yes. If the complement happens to not be open, then you can say that the original set is not closed. Okay, so right now, everything we're going to do to figure out whether or not a set A is closed or not closed, what we're going to do first is we are going to look at its complement. Okay, so we're going to look at the complement. All right, so so set A, in this case, it's this interval closed at A to infinity. They're saying that this set is closed. Why is this set closed? Well, look at its complement. What is the complement of A to infinity? It's minus infinity to A. Okay, and for this one, if it's possible to draw what the set is, now for very complicated sets, that's not always going to be true. It's not always going to be possible to draw a sketch of what the set is. But if it is possible, and it usually helps to draw a sketch, right? It can't hurt to draw a sketch, okay, to see what the set is. So this set they are talking about is this thing, right? This is the set A, and it's equal to A closed at A all the way up to infinity. They want to know, is this set closed or not? So what do? We look at the complement. So the complement is everything outside of this set. So the complement is like this. So it's open here, right? Open here, and everything go back. So the complement, A complement, is minus infinity, right? It goes all the way down to minus infinity up to A, but not including A, because the original set contains the point A. So the complement cannot contain A. So that's open at that end, right? And we know that any open interval of this form we showed yesterday is an open set. So this set here is an open set. Okay, so if the complement is an open set, right? If the complement is an open set, that means that the original set is closed. Okay, so what we have showed here is that this set is closed because its complement was open. So for now, if you want to figure out whether or not a set is closed, look at the complement, and that is the set you're going to be looking at. Okay, so these types of intervals, these half-open intervals, or however you want to call them, is a closed set. In a similar way, minus infinity up to A, where your closed at A is also closed. Why is this true? Again, just look at the complement of it. Now, what about closed interval AB? It turns out that this is a closed set. Okay, we know that open intervals are open. That's the reason why in high school, when they taught you all about it, they called open intervals, because they are open sets. But in high school, why did their high school teacher call this set or this interval? Why did they call this a closed interval? It turns out that they call this a closed interval because this set is a closed set. Okay, so it's very easy to remember for intervals. The open intervals are open and the closed intervals are closed. Okay, but how to see this? Again, if I want to know what a closed interval AB is a closed set, so again, I could draw this, so let me draw it. So here's A, and here's B. Okay, so this is closed interval AB, closed interval AB. I want to know, is this set a closed set? So what do? I look at everything outside of it. So I look at the complement of it. So here's the complement, and don't forget the right-hand side. Here's the complement as well. This goes up to plus infinity, this goes down to minus infinity. So the complement is in the red. So the complement is made up of two pieces, minus infinity up to A, union A up to plus infinity. Okay, so the complement of the set, closed interval AB, the complement of it is equal to minus infinity up to A union A infinity. And we showed yesterday that the union of open sets, okay, so I write it below, this is open and this is open, right? Open intervals are open sets. And we know that once you are unioning open sets, you are guaranteed to get an open set. So this set is open. Okay, so the complement is open, right? So again, we have this, the complement is open, therefore the original set is closed. Okay, so closed interval AB is closed since its complement is open. Okay, so we're getting we're getting our catalog of closed sets. Okay, and I put here that is closed intervals are closed sets. So closed intervals are closed sets, open intervals are open sets. Now, what about singleton sets? So for any real number x, we know that this set, the set with just one element inside of it, these are called singleton sets. These sets are closed. Again, why are they closed? Just look at the complement. So the complement is just everything outside of this set. Okay, so again, if it's possible to draw the picture, it's a good idea to do it. Okay, so here's R, and the set is just one point, X, right? That's a set, just X alone. Okay, so I'll put here, A is the singleton set, X, right? And these are called singleton sets. Now, if I want to know whether or not A is a closed set, again, look at its complement. So the complement is everything outside. So it's everything from minus infinity and everything going up to plus infinity. But remember, you do not count X, right? Because X is in the original set. So X will not be in its complement. So it's minus infinity up to X, and then you jump over X and go X up to plus infinity. So the complement of this guy, the complement of this set is minus infinity up to X union X up to plus infinity. And again, we know that these open intervals are open sets, and the union of any amount of open sets is open. So again, we have that the complement of a set is open, therefore the original set is closed. Okay, so singleton sets are closed. Sets. And I'll put here singleton sets are closed sets. On half open intervals. So A to infinity and minus infinity to A are closed sets. Okay, so these are examples of closed sets. Okay, singleton sets, closed intervals, half open intervals. These are closed sets. Okay, so what about the natural numbers? So we know that the natural numbers is not open. Okay, but is the natural numbers a closed set? Right? So what about the natural numbers? Again, we could draw this. So the natural numbers are just, so think about the natural numbers as basically infinite singleton sets, right? So it's just like the singleton set 1, union the singleton set 2, union the singleton set 3, union the singleton set 4, and so on, right? So the natural numbers, you could think of it as just the union of all these singleton sets, okay? And we know that the natural numbers is not open. Okay, the natural numbers is not an open set because the interior of the natural numbers have no interior points. Okay, so that's why it's not an open set. Now, remember, if the set is not open, you cannot then say that it's closed. But it so happens that the natural numbers is a set that is not open and closed. Okay. If I go back all the way to this first slide, you see here? So we could find sets that satisfy all these properties. A set that is both open and closed, we'll see in a bit what is that. A set that is not open and not closed, we'll see in a bit examples. A set that is open and not closed, and a set that is closed and not open. So the natural numbers fall under the last one. It's a set that is closed, but not open. Okay, so that's the natural numbers. So the natural numbers is not open, so then why is it closed? Again, look at the complement. So think of the natural numbers as just being these individual points by themselves. Okay, and the complement of it is all the spaces in between, right? But notice that we can write, so this goes down to minus infinity. We can write all these spaces in between as open intervals. Okay, all these spaces in between are just open intervals, and so on. In other words, the complement of the natural numbers is, so the first one on the leftmost side is minus infinity up to 1. Okay, that's this part here. And then this part here is open interval 1 to 2. This guy here is open interval 2 to 3. This guy here is open interval 3 to 4, and so on. So you get the idea. So then the complement of the natural numbers, I can write it as minus infinity to 1, union 1 to 2, union 2 to 3. So I'm just unioning all the spaces in between. But it turns out all the spaces in between I could write as open intervals. Okay, and what do I know about all these open intervals? Well, you know that open intervals are open sets. Okay, all these guys are open sets. So I could write the complement of the natural numbers as the infinite union of open sets. But remember, the moment you are unioning open sets, it doesn't matter how many, infinite, countable, uncountable, finite, doesn't matter. Once you union open sets, you are guaranteed to get an open set. Okay, so again, the complement is open, therefore the original set is closed. Okay, so the natural numbers is a closed set. Okay, so the natural numbers is a closed set. So the natural numbers is not open and closed. Right? Same thing for singleton sets. Singleton sets are not open and closed. So all of these sets are not open as well. Okay. So the natural numbers are closed. Yeah, so what about what is this one? This is the rationals. Well, it's the irrationals here, but I'm taking the complement of the rational. So in this example, we want to look at the whether or not the rationals is a closed set. Right? So remember, so the rationals is a set that I can't really draw, right? Because between every rational number, there's an irrational number and so on. So we can't really draw the rational numbers, but we could kind of maybe put some points here to say that these are the rationals. Let's just say. Yeah, so let's just say these are the rational numbers, Q. Now we showed that the rational numbers is not open. Okay, and that, remember, that's because if you take any rational number and you put any neighborhood around it, that neighborhood cannot be inside the rational numbers because that neighborhood will always contain an irrational number. Okay, so the rational numbers is not open. So if I want to ask myself, is the rational numbers closed? What do you have to do? You need to look at the complement. So what is the complement of Q? The complement of Q is the irrational numbers. Q complement. Q complement is the irrational numbers, right? So the red are the irrational numbers. So the irrational numbers we showed is a set that is not open. So the irrational numbers is not open. Okay. And if a set is not open, that means, so if QC is not open, that means that the original set without the complement is not closed. Okay, let me go back up here where I have that written. If the complement of a set is not open, then the original set without the complement is not closed. So that's the relationship between the rationals and the irrationals. So if I want to ask myself, is the rational number a closed set? Look at its complement. Now we've showed that the complement, which are the irrational numbers, is not an open set. So if the complement is not open, the original set without the complement is not closed. Okay, so Q is not open and Q is not closed. So the rational numbers are an example of a set that is neither an open set nor a closed set. Rational numbers, not any of them. And in a similar way, we could play the same trick with the irrational numbers. So if I want to know, what about the irrational numbers? Well, the irrational numbers we again showed, or we even used it here, is not open. Okay, the irrational numbers is not an open set. Are the irrational numbers a closed set? So again, look at the complement of it. So I know that Q is not open. So if Q is not open, then its complement is not closed. If a set is not open, the complement is not closed. Right? Maybe I should write this differently. Right? So same thing as before. So it's the same thing I'm doing here, except I'm moving the complement from this guy to this guy. So if Q is not open, then its complement is not closed. Remember, if a set is not open, its complement is not closed. So QC is not open and QC, the irrational number, is not closed. Right, so that's the argument they're making here. So same argument. So in addition to that, half open intervals, A, B, where we include one of the endpoints, these are sets that are not closed. Why are these half open intervals not closed? Again, look at the complement of them, and you'll see that the complement of them are not open sets. Right? So again, throw this one and you'll see the complement is not an open set. Now, open interval AB, this is an interesting one. Open interval AB, we know that open interval AB, of course, is an open set, but could open interval AB also be a closed set? Because remember, when it comes to set, anything goes, right? You could have sets that are open and closed at the same time. So this is our set, open interval AB, and we of course know that this is an open set. I want to know now, is this set a closed set? So we know open interval AB is open. Of course, it's a open set. I want to know, is it also a closed set? So what do? I look at the complement of it. Now the complement of it is everything outside of the set, right? So minus infinity up to A, but you include A, and B go all the way up to plus infinity, but you include B, right? So I want to know what is the complement of open interval AB. So from the diagram, that is minus infinity up to A, but I include A, right? I include A, union. So now I'm jumping over the entire open interval AB. So jump over it and go from B up to infinity, and again include B, right? So this set here and this set here, these are not open sets. These are not open sets. Why are they not open set? Because they contain, for example, they contain at least one point that is not an interior point. So I'll put here, A is not an interior point of this set. So this set is not open. Why is this set, half open interval B infinity, not an open set? Because B is not an interior point. Okay, so the moment a set has a point in it that is not an interior point, that set cannot be an open set. Open set means every single point is an interior point, right? So this set is not open, right? Because look, I found for you 1, 2 points that are not interior points. So if the complement is not open, then the original set is not closed. Okay, so open interval AB is an open set, and open interval AB is not closed. Okay, so it's not a closed set because its complement is not open. If the complement is not open, that means the original set is not closed. And again, everything that we've did so far, we talked about so far, what I'm using is this definition. Everything comes from this definition, right? If the complement of a set is open, that means the original set is closed. Or, said another way, if the complement of a set is not open, then the original set is not closed. So they are in some sense dual of each other. So they are contrasting of each other. So if a set is not closed, then the complement cannot be open, right? Or if a set is open, the complement is closed, right? So they are like dual of each other. Right, so open interval is not closed. Okay, so let's go back to this first slide. So we've met sets that satisfy most of these. So a set that is closed and not open, that's closed interval. closed interval AB is a closed set that is not open. A set that is open and not closed, that's open interval AB. Okay, so let me write that for you. Right, so it's good in this section to make like a table as you go along. So you see everything in one page. So open interval AB is open and we just showed is not closed. Okay. What about closed interval AB? We show that this is closed and not open. This is not an open set. What about the rationals and the irrational numbers? So we know that these sets are not open and not closed. So these sets are not open, and we showed just now they are also not closed. Okay, so we have a set that is open and not closed, closed, not open, not open, not closed. The last one we are missing is a set or examples. There are actually more of these, right? But we now want examples of a set that is both open. So the last one on that list is a set that is open and closed at the same time, right? Notice in what we did so far, we did not encounter any set like that was open and closed at the same time. Okay, so we're going through all four of these. So we're still looking for sets that are open and closed at the same time. Now, an example of this one is this. The empty set and the real numbers are closed. But we proved back when we were talking about the open sets that the empty set and the real numbers are open, right? We proved that the empty set and the real numbers are open. And this theorem is telling us that the empty set and the real numbers are also closed. So the empty set and the entire space, all of the real numbers, are examples of sets that are both open and closed at the same time. Right? And how to see this? So again, this proof is very easy. If I want to show, so I'll just put here, right? So a little sketch of the proof, but of course you will sit and try it. If I want to show, so required to show that the empty set is closed, right? What do? If you want to show a set is closed, look at its complement. So what is the complement of the empty set? So what is everything outside of the empty set? Now the empty set has no elements. And if we are in the real numbers, then the complement of the empty set is the entire space, the real numbers, right? So the complement of the empty set is the real numbers, but the real numbers is open. It's an open set. Okay, so R is an open set. So since the complement of this set is an open set, that means the original set is closed. Right? So that is why the empty set is closed, because its complement, look, its complement is this guy right here, right? And again, you can play the same trick. Why is the real numbers a closed set? Well, what is the complement of the real numbers? Look, it's this guy right here. The complement of the real numbers is the empty set, and the empty set is open. Therefore, the original set is closed. Right? So in order to prove that the empty set and the real numbers are closed, you just jump between them by taking complements. Okay, and that actually gives a hint on how to prove this result here, the second one, and the third one. So the proof of this one is left as an exercise because if you look back previously, there was a theorem about open sets, and given open sets, how to make more open sets. So I'll write it here. So we see them side by side. Okay, so for open sets, right, so for open sets, the arbitrary union, so any union, arbitrary union of open sets is open. So if you take any union of open sets, you got an open set, right? So we proved this, I think, yeah, yesterday we proved this. And we also proved that the finite intersection of open sets is an open set. It's open. The arbitrary union of open set is open. And we proved that the finite intersection of open sets is open. Okay. What this term is saying is the complement of this. So if you take the complement of these results, of course, it's not, you can't just say take the complement, right? You have to sit down and actually write out the sets, then take the complement of each one, then apply De Morgan's law, right? So, but this term is basically the complement of this one for open sets. So for closed sets, so if I have closed sets, how do I make more of them? All right, so the same theorem, but on the side of the closed sets is the reverse or the converse or the complement, however you want to look at it, or maybe the opposite is a way that you interpret it as, right? Because so far there's a relationship between the open sets and the closed sets, right? They are complements of each other. So for closed sets, the arbitrary, not union, what is the complement of union? Intersection, right? So on the side of closed sets, you have intersection. So over here is the arbitrary union. For closed sets is arbitrary intersection of closed sets is closed. Right? It's closed. And what about finite now? So for on the side of the open sets, finite intersection of open is open. But if we are on the closed side, it becomes finite. What is the complement of intersection? The complement of intersection is union, right? So I'm using De Morgan's law. Finite union of closed sets is closed. It's closed. Right? So this is the relationship. You need to know this, by the way, and you need to know how to prove both sides, right? So for open sets, once you are unioning open sets, you are guaranteed to get an open set. It does not matter how much union you do. That's what arbitrary means. Countable, uncountable, finite, infinite, it doesn't matter. Once you union open sets together, you get an open set. Now, for closed sets, once you intersection any amount of closed sets, so you could do finite intersection, infinite intersection, countable, uncountable, doesn't matter. Once you intersect closed sets, you are guaranteed to get a closed set. Now on the side of open sets, once you do finite intersection of open sets, only then are you guaranteed an open set. On the side of closed sets, once you do finite union, only then are you guaranteed a closed set, right? So you see they are complements of each other. And in order to prove this, so you should sit and try to prove this. This is very important. If you get stuck, I have these solutions up, I think, or you could find the proof of this that in any textbook, or you could just search this on the internet and you'll see proofs of it, right? All of the proofs is the same. You need to apply, so to prove, apply the Morgan's law, right? And of course, what is the Morgan's law? Do you all remember that one? That one says that, so I'll give you it for two sets, but it extends to any number of sets, but I'll just write it for two sets. Maybe then you'll remember it. A union B complement is the same thing as A complement intersection B complement, right? So hopefully now it's ringing some bells. And A intersection B complement is the same thing as A complement union B complement, right? So these were De Morgan's law. Okay, so you should sit and try to prove this. Right, so now we know once we have closed sets, how to make more. You are allowed to intersect any amount of them together and you will get a closed set. Or if you want, you could intersect finitely many and you will get a closed set. Now, that does not mean that if you, you union finitely many and you get a closed set. Now, that does not mean if you union, so you might be thinking, what if I union infinite amount of closed sets? Will I get a closed set? And the answer is, it depends. You are only guaranteed to get a closed set if you union finitely many closed sets. If you union infinitely many closed sets, you may or may not get a closed set. It depends on what you are unioning. Okay, so you may or may not get it. Now, the first part here, the empty set and the real numbers are closed sets. But we also saw that the empty set and the real numbers were open sets, right? Okay, so I put here, how does this result compare to the union and intersection for open sets, right? So that's this little table that I drew here. Okay, so that's how it compares. And I put here that the empty set and the real numbers, we already saw these were open sets, but this term is saying that they are also closed sets. So the question is, are there any others? So in the real numbers, where we are studying all of this, the empty set and the real numbers are both open and closed. Are there any other sets in the real numbers that are also open and closed? The answer is no. If I asked you in an exam, well, we are in this standard topology, but I wouldn't put any exam, right? Because for you all, this is the only topology you know about. And I ask you, give an example of a set in the real numbers or something like that, that is both open and closed. You only have one of two choices to give me. You could either give me the empty set or the real numbers. If you try to think hard about any other third set that is both open and closed, you'll run out of time in the exam because there are no other sets that are both open and closed. Only these two guys, okay? With the topology you all know, right? Now, we also saw that the rationals and the irrationals are neither open nor closed. So they are not open and they are not closed sets, right? And again, are there any others? Are there any other subsets of real numbers that are both, that are not open and not closed at the same time? And the answer is yes, right? So it's not like the first case with the empty set and real numbers. For example, just take the rational numbers between 0 and 1. So this set represents all of the rational numbers, right? But what if you just take the rational numbers between 0 and 1? So what I'm saying is the empty set and the real numbers are the only open and closed set. Right? So we know that the rationals is not open and not closed. My question is, are there any other sets in the real numbers that have this property? And the answer is yes, right? So check. I shouldn't say check. Another example. Are the rational numbers. So just pick the rational numbers between any two real numbers you want. So rational numbers between, right? There are so many other sets that are not open and not closed. Rational numbers between, let's say 0 and 1, let's just say, right? This set is also not open and not closed. So any infinite subset of the rational numbers or any infinite subset of irrational numbers are also not open and not closed. How to write this in set notation? The rational numbers intersection 0, 1. Okay, that's how to say the rational numbers between 0 and 1. Okay, so this is another example. Or you could pick the rational numbers between any two of your favorite number. It doesn't have to be 0 and 1. It could be minus pi and pi, right? Anything. Okay. All right, so the next part deals with this thing called nested set. So we want to basically just show you all. It's a very useful result later on. Is something called the nested interval property of R. So in order to explain that result for you, the nested interval property, I need to tell you what a nested interval is. And in order to tell you what a nested interval is, I need to tell you what is a nested set or a nested collection. Okay, so that's what this definition is. So let this fancy A just be a countable collection of non-empty subsets of R. So A1, A2, A3, and you keep going. That's what this collection is. We say that this collection, fancy A, is a nested collection if the nth plus 1 set is contained in the nth set. So every set is contained in the guy before them, right? And if that definition there looks kind of complicated, the picture is very easy, right? So nested sets. Right, so here's the diagram of a nested set. So this is just for any set, not necessarily an interval, just any sets. Right, so this is A1, A2 is inside. This is A2. Where's A3? Inside A3. Okay, so you get the idea. This is what nested means. Each set is inside the previous one. And this guy here is A4, right? And you keep going. And you keep going. So nested sets means the n plus 1 set is contained in the nth set, right? Or if you want to write it like this, A1 contains A2 contains A3 contains A4 and so on. So that's essentially what nested means, one inside the next. right? Or equivalently, if AM is a subset of AN, whenever M is bigger than N. So this second condition, AM subset of AN, all that is saying, that's another way of saying that two sets are nested, because, so from this example, from this picture that I have here, right? Notice that A4 is contained in A2, right? Here's A4, and here's A2. So all that part there is saying is that, or AM is contained in AN whenever M is bigger than N, right? So you see 4 is bigger than 2, so that means A4 must be contained in A2. In other words, the set with the higher number is contained in the set with a lower number, right? So you could either choose to write it like this, or you could choose to write it like this, whenever M is bigger than N, right? So that's what that part they're saying. Okay. Right, so for example, if A is a nested collection of sets, then we have this relationship. The n+1 set is contained in the n set, and we get this chain all the way down. A4 is contained in A3, A3 is contained in A2, A2 is contained in A1. So A1 is the largest set. Everything is contained in A1, and the sets are just decreasing. So this is a nested collection of sets A. Now, if it so happens that all of these A's, because I didn't tell you what these A's were, all I said is that these A's, AN, A1, A2, A3, and so on, all we know is that they are non-empty subsets of R. If it so happens that these A's, they are all intervals, then we get this result. This is called the nested interval property in R. And the proof, well, it's put here as left as an exercise, but maybe this proof is too difficult to figure out on your own. So the proof, I'll put where to find the proof if you're interested in seeing it, right? It's a bit involved. So the nested interval property. Okay, so you don't need to know the proof, but you should know the statement of the result, right? Because I could ask you I could ask you what is a nested interval property in R, right? And then you have to write this result for me. So for proof, C, I think it's 2.5.2 in the bottle, right? So that's one of the reference texts. I think it's called Introduction to Real Analysis. But yeah, do not need to know the proof, right? You don't need to know the proof. It's too long to get tested on now, right? But in postgrad, you might get it. So if you're doing postgraduate real analysis, you might have to do this proof as part of a question. Yeah. All right. So if you're interested in seeing the proof, you could check this textbook for it. So what exactly is this thing? So the nested interval property in R, I'll just give you the sketch of it, and then we'll look at what the exact statement is. So it's just saying that if we are in the real numbers and we have a nested, so we know what nested collection is. It means each set is contained in the guy before. But this one is saying not only are these sets nested, they are intervals. So for example, this interval is your A1, and all the other intervals are nested inside of it. So if this interval is A1, maybe A2 is, I don't know, maybe A2 is somewhere here, right? So that guy's A2. And A3 is maybe over here. Maybe A3 is over here. And A4 is maybe this guy here is A4, and so on, right? So you have a collection of nested intervals. The nested interval property says that if you intersect all these guys together, so this says if we have a collection, so instead of an, I'm going to call them in, right? Where in are the intervals. Right? So maybe I should have, instead of calling it A4, A3, A2, A1, maybe I should have called it I. Right? But it's the same sets. I'm just calling them I for interval. Right? So I for interval. So this is a nested collection of, so you see, I didn't put the I drew the wrong type of interval because if it's open interval, it doesn't work. And that's the collection of these intervals need to be compact. They need to be closed and bounded. That's an interval of closed and bounded intervals. Right? So I drew the wrong thing. How I drew it here, well, how I drew it here is correct, but the interval should be closed. Right? So the intervals need to be closed intervals for this to work. So here's I2, here's I3, here's I4, and so on. Right? So the intervals are closed. So closed, so it's a nested collection of closed and bounded intervals. This is saying if you intersect all these guys together, then the intersection of all these intervals is non-empty. Right? In other words, if you have a nested collection of intervals that are closed and bounded, so the closed and bounded intervals are just closed intervals. So these are just the closed intervals you all know of. So maybe 0, 1, 0.5. Then maybe the next one is 0, 1/4, right? So that's what these intervals look like. This is saying if you intersect all of these intervals together, there is at least one element inside of it. In fact, you could show, so the nested interval property just says that the intersection is non-empty. But I'll put here, in fact, you can show, right? So you'll see the proof in the battle for this. You can show that not only is the intersection non-empty, there is only one element in the intersection, right? So the nested interval property just says that this intersection is non-empty. Non-empty means it contains at least one element in the intersection of all of this. So all of these intervals have one element in common, at least one element. What I'm saying is that you can not only show that they contain at least one element in common, you could show that they contain exactly one element in common. There's only one element in here. Right? There's only one X in there. Right? And it's actually a very useful result. Right? I don't think we use it again in this course, but it's used and proven many other things. Right? So we have it over here, the nested interval property in R. Let In be a nested sequence, so you could say nested collection of non-empty closed and bounded intervals in R. So they need to be closed and bounded. right? Then the intersection is non-empty. Okay, so again, you don't need to know the proof of it, even though it has proof exercise. I need to change that. You don't need to know the proof of it, but you should at least look at the proof of it, right? This condition where the intervals are closed, so we know what closed means, closed set. And remember what bounded means? A set is bounded if it has an upper bound and a lower bound, right? So bounded simply means the intervals do not extend to infinity. Okay. This condition of being closed and bounded, we will come back to it at the end of this section. This is together. This is a fancy way of saying these sets are something that we call compact sets, right? We'll see later on in this chapter that closed and bounded sets in the real numbers means you are a compact set. Okay. So let's get into our property. So now we could get into the idea of what a limit point is, right? So eventually when we go to take limits and we write the limit as x approaches a, that point that you are approaching cannot just be any point. That point we will see later on has to be what is known as a limit point, right? So let A be a subset of R. A point X belonging to R is a limit point, or sometimes we say an accumulation point of the set A if, so here's the condition, every deleted neighborhood of X contains a point of A. Okay, so how to write this? Another way of writing this means for every radius, epsilon, the deleted neighborhood around that point X of that radius, intersection A is non-empty. In other words, for every radius you choose, the deleted neighborhood and the set A have a point in common. So how to say two sets have at least a point in common? Another way of saying that is that the intersection of them is not empty, right? The intersection, not empty, means they have some point in common. So why are we using the deleted neighborhood here? Remember, the deleted neighborhood simply means you are not allowed to choose X. So this is saying they have a point in common, but that point is not X, right? So that point is not X. So what else to point out from this definition? Okay, so let me give you the picture of this, right? So everything that deals with closed sets has to actually talk about limit points, right? So yes, we are in the real numbers, but again, the way I usually find it easier to understand is by looking at like a 2D picture of it. So let's just say this is a set A. Let's go back to interior point for a moment. So let's just look at an interior point. So we say A is an interior point of this set if, so remember what the picture looked like, if it is possible to put a neighborhood around it, right, of some radius, call it epsilon, such that that neighborhood centered at A of radius epsilon lies entirely within the set, right? That is what it meant for A to be an interior point, or A belongs to the interior. So that's an interior point. Interior point means you need to find just one neighborhood. Just one neighborhood around that point inside the set. A limit point is very different to this, right? A limit point is very different. A limit point means, so let's use, so first of all, the first main difference between an interior point and a limit point is you see the interior point must first belong to the set A, right? An interior point of a set must first be an element of that set, right? Because I'm not going to look for an A all the way outside the set here, right? I could only look for a set, an interior point by looking at the elements inside the set. A limit point does not even need to belong to the set. A limit point may or may not belong to the set. It doesn't matter. Okay, but sometimes it belongs to the set, sometimes it does not belong to the set. For this example, I'm going to put the limit point inside the set, right? But it doesn't always have to be like this. Okay, so I'm going to put the limit point here, x. In this case, the limit point is inside the set, but x could have been maybe on the boundary or something. Okay, so what does it mean to be a limit point? A limit point means, so unlike an interior point where you are searching for one neighborhood, a limit point means every single neighborhood you put around this point X, every single neighborhood, right? No matter how big or how small. So here's a very big neighborhood, right? It's a very big neighborhood. Or maybe you do like a very small neighborhood. It doesn't matter. Every single neighborhood you put around this point must contain at least one element of A, not including X, right? Because you see in this case, if I said every neighborhood around this point must include an element of A, then if you're clever, you will say, well, just take X. X is an element of A. And we know that X, the center, is always in its neighborhood, right? So every neighborhood contains X, and X is an element of A. Therefore, every neighborhood will contain an element of the set A, right? But the added restriction, the reason why we are not using full neighborhoods, why we are using deleted neighborhoods, is that we do not want you to say, hey, just choose X. We are looking for another point of A, right? And there are so many, right? Look how many points of A are in here, right? So no matter how much I shrink, so think of it like you put a big neighborhood and now you're shrinking this neighborhood, you're shrinking the radius. No matter how small you make this radius, so you're making the radius even smaller, there will always be a point, an element of A somewhere in there, not including X. You're not allowed to choose X. That is the meaning of a limit point. Okay, so interior point. So if you take one thing away from this class, it's this one. Interior point means you are looking for one neighborhood, just one of them, completely within the set. You are inside it. Limit point means every single neighborhood you put around this point, no matter how large or how small, must contain some element of that set, not including the center. Okay. And you see over here, you might be saying, but look, half of the neighborhood is falling outside of the set A, right? Are we allowed to do that? The answer is yes. You see, for interior point, the neighborhood must lie entirely within the set. For a limit point, I didn't say the neighborhood have to always be inside the set A, right? That's the power of the limit point. For a limit point, yes, we need every single neighborhood to contain an element of the set A, but the neighborhoods could fall outside of A, right? The neighborhoods do not have to be all inside of A, right? They could fall outside of A. Look, they could fall outside of A. That's fine. We don't care. All I want is that when I take a neighborhood, so I delete a neighborhood, because I'm not allowed to choose the center. So just remember, that's why they do delete a neighborhood. You're not allowed to choose the center. So all that means is that for any radius, the deleted neighborhood around that point of any radius contains an element in common with A. How to say that? The intersection of the deleted neighborhood and A is non-empty. There's an element in there. And there might be infinitely many, I don't know, but there is at least one element in there. That is what a limit point is. So X is a limit point of A. So limit points and interior points are different, very different ideas. Okay. Interior point means you are looking for neighborhoods completely inside the set. Limit points mean every single neighborhood you draw or you make, it might fall outside, half of it might fall inside, it doesn't matter, but every single one you make must have an element of A somewhere in there. Okay. So that is the idea between interior points and the limit points. Now, just like with interior points, if I take all the interior points and I put it in a set, remember that's what this set is. The interior of A is the collection or the set of all interior points. So in a similar way, I could collect all the limit points of A, collect all the limit points of A and throw that into a set. So the set of all limit points of A is called, so it's not called the limit point set, it's called the derived set. The derived set of A, right? And it's given the notation A prime. Okay, so that's why in this course, for complement, we were using AC for complement, right? I know some of you may have also used A prime as the complement, so some of you were using the same thing. But in this course, we are using AC as complement, so don't put A prime. A prime in this course means this, the derived set. Okay, so A prime and AC means two different things in this course. Okay, so that's the set of all limit points. We call it the derived set. So before we move on, let me give you an example of a point that is not a limit point. So X here is a limit point. In fact, this point here, A, is also a limit point. What about this point up here, Y? Is Y a limit point? So Y is now like on the boundary. And the answer is yes, because look, any neighborhood I put around Y, no matter how small or how big, yes, half of it is falling outside of the set. That does not matter. Every single neighborhood contains a point of A somewhere in there, right? That's all I want. So Y is a limit point. Which point is not a limit point? What about this one out here? Let's call this point Z. Is Z a limit point of A? Well, again, what does limit point means? Limit point means every neighborhood around Z must contain at least one point of A, not including Z. What about this neighborhood? This neighborhood. Does this neighborhood contain any point of A? No, there's no point of A in this neighborhood. So this guy, Z, is not a limit point. So limit point, I'll maybe write it as LP. Okay, maybe spell it out for now. It's not a limit point of A. Why is it not a limit point of A? Because it is possible. Yes, I know if I take a neighborhood this big, if I take a neighborhood like this, then okay, look, I have points of A in here, that's fine. But in order for it to be a limit point, every single neighborhood must contain a point of A. So what about if I take a neighborhood very, very close to Z, very small? There's no point of A inside of this neighborhood. Okay, so it is not a limit point. Right. Right, so that's the definition that we went through. And like I said, the set of all limit points is called the derived set of A, and is denoted by A prime. Yeah, so if now the limit point, remember I said the limit point may or may not belong to the set. Right? So the limit point may or may not belong to the set. It's just it could be any real number. If it so happens that you have a point belonging to the set, but that point is not a limit point, right? So if you have a point in a set, let's go back to the picture, right? So this guy is a limit point, this guy was a limit point, this guy was a limit point. If it happens that there's a point so this diagram doesn't have it, but I'll just show you. If it happens that you have a point somewhere in the set that belongs to A, but is not a limit point, we say that point is an isolated point. Okay, so that's what this is saying. If you have a point belonging to that set and that point is not a limit point, then we say that point is an isolated point. Isolated means, why are they using the word isolated? Isolated means if you are not a limit point, then you could put a neighborhood around that point that doesn't have anything of A, right? That's what it means if you are not a limit point. So X does not belong to the derived set means you are not a limit point. Not a limit point means that you could put a neighborhood around that point that doesn't have anything in A. So that is why X is isolated from A, right? It's an isolated point of A. It's all out there by itself. Okay. Right, I put a limit point of A may or may not belong to the set A. How does this differ from interior points? Interior points must also belong to the set A. Limit points may or may not belong to the set. Right? So it turns out that there is a relationship between remember what this symbol is? A with a little circle. This is the interior. So there's a relationship between the interior of A and the limit point of A, right? And that is every interior point is a limit point. Okay, every interior point is a limit point, or the interior of A belongs to the derived set. And how to show this? Very easy, because how do you show one set is a subset of another? So suppose X belongs to the first set, right? So suppose X is in this first set. We need to show X belongs to the second set. So if X belongs to the interior, right? A with this little circle is the interior. Let me write that here, right? So another way of writing the interior of A is A with a little circle, okay? So suppose X belongs to the interior of A. So by definition, all we're doing is we're just applying definitions. So that means X is an interior point. Interior point means there exists some radius, so let's call it delta, such that the neighborhood around X of that radius is entirely within A, right? That's what it means to be an interior point. Now, what I want to do is show that every neighborhood around X contains a point of A, right? So now I need to choose an epsilon. So how am I going to choose this epsilon? So let epsilon be, so it has to hold for any epsilon. So let epsilon be any other radius. Then either epsilon is smaller than this delta, or it's bigger than this delta, right? Either epsilon, so if delta is 5, let's just say if delta is 5, either epsilon is smaller than 5 or it's bigger than 5. So in both cases, let's see what happens. If the epsilon happens to be less than delta, then what I could do is, so it might be better if I write this one out. Okay, let's do it this way. Yeah, so I want to show you all how they got this line. See. Okay, yeah. Right, so I just want to show you all how you do this calculation, because you don't need to cram up this. Right, so this line over here, what are they doing here? So in this case, if epsilon is less than delta, right? Then remember, what do I want to show? I want to show that this X, we know that this X is an interior point. I want to show that this X is also a limit point. In order to show an element is a limit point, I need to show that the deleted neighborhood around that point of any radius intersection A is non-empty, right? So this is where I start with, right? That's what I'm starting with over here. Now notice that the deleted neighborhood is always contained in the full neighborhood, right? So why is that true? So think about this. If you have if you have two sets, actually we don't need to go through all of that. The relationship between the deleted neighborhood and the original neighborhood, the deleted neighborhood is the original neighborhood, but you remove a point, right? So obviously the deleted neighborhood will be contained in the full neighborhood, right? Because the deleted neighborhood is this guy minus X without X, right? And what do I know? I know that epsilon is less than delta. So if epsilon is less than delta, then the neighborhood centered at X of radius epsilon is contained in the neighborhood centered at X of radius delta, right? So think circles. So what if this one has a radius of, let's say 2, and this one has a radius of, let's say 5? Then obviously the circle of center X of radius 2 is contained in the circle of center X radius 5, right? And I know that this delta neighborhood is contained in E. So this delta neighborhood is contained in E. So that's how we got this first part here. Okay. But what do I want? I want the intersection of this guy with A. So intersect both sides with A. Right. So from here, what I'm going to do now is I'm just going to take this part and this part. So from here, I know that the deleted neighborhood, center at X, radius epsilon is contained in A. So ignore the middle two, ignore these middle two neighborhoods, right? Intersect both sides with E, right? So intersect the left-hand side with E is subset of A intersect with E, right? So intersect both sides with E. A intersect A is A, right? A intersect A is A, right? So this thing is is contained in A. Right? Okay. All right, sorry about that. It's actually easier than that. So it's actually easier than that. So from there, so all they're saying now is that this neighborhood is inside of A. So let's draw a picture of this. So this here is A, and here is X. Here's epsilon. So this thing is the deleted neighborhood, centered X of radius epsilon. So all they're saying is that this deleted neighborhood is inside of A. So therefore, if this neighborhood is inside of A, what happens when you intersect it with A? So when you intersect it with A, right, if X is contained in Y, then X intersection Y is X. Right? So draw the diagram for that. X is contained in Y, then X intersection Y is just X. So if the deleted neighborhood is contained in A, then the deleted neighborhood intersection A is just the deleted neighborhood. Okay. And the deleted neighborhood is not empty, right? Because these are intervals. They have uncountably many points. So what did we show? We showed that if epsilon is less than delta, then the deleted neighborhood around that point, intersection A, is non-empty. In other words, X is a limit point of A, right? And that is when epsilon is less than delta. Now we need to show what happens if epsilon is bigger than delta. Okay. So if epsilon is bigger than delta, again, they're doing the same sort of argument, then the neighborhood centered at X of radius delta is contained in the neighborhood centered of X of radius epsilon, right? Because epsilon is a bigger one. So epsilon is the circle with the bigger radius. So we get this inclusion. Now remove X from both of them. Okay, so if I remove the center from both of them, then the subset relationship still holds. So I get the deleted neighborhood around X of radius delta is contained in the deleted neighborhood around X of radius epsilon. Now intersect both sides with A. Yeah, so this is the one where you intersect both sides with A. So intersection both sides with A, okay. And since this guy, the deleted neighborhood around X of radius delta is a subset of the full neighborhood, and I know that the full neighborhood was contained in A, right? Then this left-hand side, right? This left-hand side, which is this left-hand side is simply the deleted neighborhood centered at X of radius delta. Okay, again, it's if X is a subset of Y, what is X intersection Y? It's equal to X, right? So that's the same result they're using here. And so this left-hand side simplifies to just the deleted neighborhood around delta, which is a subset of the deleted neighborhood of radius epsilon intersection A. And I know that this one cannot be empty. Why can't this set here not be empty? Because look, it contains inside of it a deleted neighborhood. If I tell you a set contains inside of it open interval 0, 1, right? So I tell you I have a set A, it contains inside of it open interval 0, 1. Is the set A empty? No, how could it be empty and it contains open interval 0, 1? Same idea here. This is the set. So this set here contains inside of it this deleted neighborhood. Remember, our deleted neighborhood is just the union of two open intervals. Okay, so the deleted neighborhood contains inside of it essentially an interval, right? So this deleted neighborhood intersection A cannot be empty, right? It's not empty. And that is what I want to prove, right? Hence, for any epsilon, the deleted neighborhood centered X, radius epsilon, intersection A is never empty. In other words, X is a limit point of A, right? So I put here, so maybe this one might be easier. You should try to prove this theorem using the contrapositive, right? So the contrapositive means if X is not a limit point, then X is not in the interior. Right? So maybe I might put that one on your next assignment. Right? So what we proved here is, that the interior of a set is contained in the derived set. That is, every interior point, so all of this is taking place in R, by the way. Every interior point is a limit point, right? In other words, if X belongs to the interior, then X belongs to the derived set. What I'm saying is, try to prove instead. So instead of that proof, right? So that whole proof was to prove this result. Try to prove instead the contrapositive. Right? So I hope you'll remember what contrapositive means. So contrapositive means if P then Q, the contrapositive is, so the contrapositive is an equivalent way. Another way of saying if P then Q is if not Q, then not P. Okay, so this guy is P, this guy is Q. So what is the contrapositive? If not Q. So if X is not a limit point, then, so if not Q, then not P. Then X is not a interior point. So both these things are the same, right? These two things are the same. Or we say they are equivalent. So maybe I said to prove that because maybe the contrapositive is easier to prove. I don't know, right? I suspect the contrapositive may have been easier to prove. So try to prove this statement instead. Okay, so is it then true? So we know that the interior, every interior point is a limit point. What about the converse? Is every limit point an interior point? And I put here, this is not true. So the converse is not true, right? That means there may be limit points of a set which are not interior points. For example, if the set A is open interval AB, then we know that the interior of A, so this is an open set, right? Open interval means open set. So the interior of our open set is equal to the original set. That's what it means to be open. So the interior of A is open interval AB, and open interval AB is contained in the derived set as expected. So you could show that every point in AB, open interval AB, is indeed a limit point. You could show that. But why then is the derived set not a subset also of the interior point? So this means that there are limit points of this set that are not interior points, right? However, A and B, you could show, are limit points of A, but they are not interior points of A, okay, since they do not belong to A, right? So this is a good example to show that the converse, let me go all the way back to it, that the converse of this theorem is not true. So every interior point is a limit point. That is true. However, is every limit point an interior point? No. Right? This is an example. In this example, A and B are limit points of the set, but they are not interior points of the set. Right? Okay, so last set of definitions. So what is an exterior point? So a point X not belonging to A, right? So a point X, if you do not belong to A, you belong to a complement. So a point X not belonging to A is said to be an exterior point of A if there is some radius such that the neighborhood around that point of that radius is entirely contained in a complement, right? So this definition should look very similar to the definition of an interior point, but it's the interior point on the complement side. That is, X is an exterior point of A if X is an interior point of the complement, right? And the set of all exterior points of A is called the exterior of A, denoted by EXT of A, right? So let me just give you the picture for that. So again, we have some set A, right? This is the interior, right? So this is the interior of A. The exterior of A is the interior of the complement. So it's a little bit confusing, I know. So what is an exterior point? X is an exterior point if X must first not be in A. If X is not in A, what is another way to write that? Another way to write that is X belongs to A complement. And there is some radius such that if I put a neighborhood around X of that radius, I fall inside of the complement. So let's look at X. Notice if I put a neighborhood, if I put this epsilon neighborhood, right, around X, notice that you are entirely within A complement. Where is A complement? This is A complement, right? A is the set, so A complement is everything outside. So notice that this neighborhood is entirely within A complement. So X is an exterior point of A. In other words, we say X belongs to the exterior of A, right? But if you understand the definition of an interior point very well, then you could see that this is just saying, in other words, X is an interior point of which set? Of the complement. So X is an interior point of the complement set because the complement of a set is a set, right? A is a set, A complement is a set. The interior points of the complement is what is called the exterior. So I'll put here, the exterior of a set is equal to, it's the same thing as the interior of the complement. Okay. And the last definition has to do with what are called boundary points. So a point X belonging to R is said to be a boundary point or a frontier point of a set A. If for every neighborhood, every epsilon, so every neighborhood you put around that point, this neighborhood is going to contain points of A as well as points of A complement. So think about if you're sitting like on a wall or like if you're on a fence. If you move to the left of you, you're inside, and to the right of you, you're outside, right? So you're on the boundary. Okay, so what is an example of a boundary point? So what if you're over here? This point. Let's call it Y. Notice if you put any neighborhood around Y, any neighborhood you put, no matter how big or how small, will contain points of A complement and it will contain points of A, right? So therefore, so Y is a boundary point of A. And we say, if you're a boundary point of A, we say Y belongs to the boundary of A. So how to write the boundary? They usually denoted by the symbol, or Y belong to BD of A. Any way you want to write it. So these are the boundary points. Boundary points mean once you put an interval around it, to the left and to the right, one side you contain points of the set A, and on the other side you contain points of A complement. So you are on the boundary. So all of these are boundary points. All of these are boundary points of A. Okay, the interior is not a boundary point. The exterior is not a boundary point. Okay, so you need to know all these definitions very well. Right, so the set of all boundary points is called the boundary or the frontier of A, and denoted either by BD of A or this fancy symbol, sometimes they call it del of A, or FR of A for frontier. And this is the picture you should have in your head. So given any set A, the interior is the part inside, the exterior is the part outside, and the boundary is the set in between. Right? So this is the idea you should have for the relationship between the interior, the exterior, and the boundary. Okay, so we'll stop there for today. So in our next class, we'll continue from here. We'll look at some properties of the interior, exterior, boundary, and limit point, how they interact together. Okay. Okay, are there any questions?